a presentation on the Fragile Soil Index interpretation, and I have about 14 slides, so it shouldn't take too long. And since we're on a teleconference, so we can stop and discuss things, and you can ask questions during the presentation if you want to do that. Okay, so how that all got started, the Fragile Soil Index, is I was asked to write a white paper on a fragile soil index, and it was to be an alternative to the vulnerability, the soil vulnerability index, and that's live and well today and going well, that vulnerability index. And then later we developed the fragile soil index interpretation based on that white paper. So for the white paper, I was hoping I could just go to the literature and I could find a fragile soil index. So when I reviewed the literature, I really couldn't find anything. There was a lot of references to fragile soils, fragile landscapes, and fragile ecosystems, and there were some indexes for fragile ecosystems. So using that information, I kind of developed a fragile soil index. So fragile soils. This is how I'm defining fragile soils. It's those soils that are most vulnerable to degradation. So they're easily degraded, they have a low resistance to a disturbance, and they have a high susceptibility to erosion with low resilience. So when I was reviewing the soils in the literature, when they referred to fragile soils, these were the characteristics that were used to describe them. I mean, they had low organic matter contents, they had low water stable aggregates, they were absent of soil structure, they were on sloping ground, they were in arid and semi-arid regions, they had sparse plant cover, and they had low biodiversity. So I used these characteristics and used them as indicators for the index. And we'll go through those. I originally had biodiversity as one of those indicators, but I couldn't deal with it in Nasus. We didn't have enough information to actually deal with that, so I didn't use that. But here are the first three indicators that I'm using. I got organic matter content, indicates the capacity of the soil to resist and to recover from degradation processes. So as organic matter increases, the soil is less vulnerable to soil degradation. And then I have aggregate stability or soil structure. And that indicates the capacity of the soil to resist degradation, such as from accelerated erosion. So as aggregate stability increases, the soil is less vulnerable to degradation. Then I have rooting depth or soil depth. Shallow soils are more vulnerable to degradation because they have a limited rooting depth and have a reduced capacity to generate new soil. So those are the first three. Okay, there's a total of 6 indicators in total. These are the last 3. And I chose vegetation cover because uncovered soil is vulnerable to the process of soil erosion, both by wind and water. So as vegetation cover increases, it's less vulnerable to degradation. Then I have slope. Sloping ground is more vulnerable to the process of water erosion and also to mass movement. So as slope increases, we have an increase in the vulnerability. And then I chose aridity, because lack of water is the main factor limiting biological processes and the capacity to recover. So susceptibility to degradation increases with aridity. So increase aridity, increase the vulnerability to degradation. So those are the indicators that I chose for the index. So this is the index here. It's just a simple additive index. That's a fragile soil index. You can see I've got the 6 indicators there, and I have a weighting system. The aridity index there at the end is weighted 3 times. The vegetative cover and slope are weighted twice. And the indicator data are converted to a relative value ranging from 0 to 1 using a scoring curve, and I'll go through each one of those. And then the standardized scores are then weighted. And the index values, they range from 0 to 1, with 1 being the most fragile. And the 0 to 1 rating is consistent with how interpretations are developed in Nasus, our soil database. So this is the index. And I just wanted to go over briefly Nasus interpretations and how they work, because some of you may not be familiar with them. So let me get the pointer out. So we have 3 components to interpretations in Nasus. We have properties over here, then we got evaluations, and then we got rules. And these are the 3 building blocks to our interpretations in Nasus. We can have many rules to a primary rule, and you can have a few evaluations that go to a rule, and then we got our property. Now the properties, what those are, is their SQL script, and they query the database and get the property from the database. And they'll perform some kind of function. In this case, we're querying for linear extensibility percent, LEP, it's an indicator of shrink swell, and we want a weighted average between 25 and 150 centimeters, or above a restriction. So the result of that property is sent to an evaluation, and it's given a membership value right here, between 0 and 1. It's given a membership value. And 6 was sent, the result of the property was sent to the evaluation, so the membership value would be 1 in this particular example. And then that is sent to the rule and given a reason, or the rating classes, and it's considered a high shrink swell soil. So then up here in the primary rule, right here, where it's combined with other rules of the interpretation, the final interpretation would be that the soil has limitations for dwellings with basements because it has a high shrink swell soil, because it is a high shrink swell soil. So this is how interpretations work in Nasus, and I will be using this for the index. Okay. This is what the fragile index interpretation looks like in Nasus when you open up the primary rule. Okay, each one of these square boxes here, that is a rule, and it contains, the rating, all the information for that particular indicator. And over here we have the hedges. You can see here's the multiplier, the weighting system. And then we've got the operator over here, which is the sum, which adds the result of each one of those rules. And if we were live and in Nasus, we could drill down into each one of these rules. We could see the rating classes, we could view the evaluation, and we could look at the property script that queries the database. So this is our first rule, or first property or indicator that we're going to look at. And so what I have here is the property that's querying the database is going to be organic matter, and we're only going to look at organic matter in the surface layer, the A horizon. And okay, right here, this is the screenshot of the evaluation, and it gives it a membership value between 0 and 1. And this curve, the scoring curve, I was looking for the maximum inherent potential for organic matter for the U.S., and the Northeast has pretty high organic matter contents. So I used the Cornell Soil Health Assessment, the medium curve for organic matter. So that's this curve here. So it evaluates organic matter from 0 to 7%. Anything greater than 7% is given a score of 0, meaning it's not fragile. Score of 1, it's highly fragile. So that's how that works. And then down here in the table, the interpretive ratings for organic matter. Okay, this would be contained in the rule. And these are the rating classes. I have 6 classes from extremely low organic matter all the way up to very high organic matter. I broke it out. These are the class limits. Right here are the class limits. And this is just the boundary from the scoring curve. And what this information over here, the equation, that's just an equation of the scoring curve up in the evaluation. That's just so you could program this into an Excel spreadsheet and just run it there, and wouldn't have to run the interpretation if you want to do site-specific stuff. Okay, this is the next indicator. And in Nasus, we do not have a field for aggregate stability or any kind of aggregation. But we do have soil structure. And the soil structure is well populated for the A horizons. So I use soil structure. And since soil structure is a kind of a discrete variable, it's not continuous, I had to do something a little different. And over here, this table 3 on the left side there. Okay, this table comes from the Soil Quality Morphology Index that Bob Grossman developed. And he tended to group things and put things in classes. And he grouped them that would provide the best physical condition for plant growth. So he grouped soil structure that would provide the best physical condition for plant growth. So 5 is the best, like the best soil quality, and number 1 would be the poor soil quality based on the structure. So I programmed this into the property. So I just used just a linear scoring curve over here, and then so the class 1 gets assigned 1, meaning it's highly fragile, poor quality, poor soil structure. 5, the best, not fragile. So then down here in the interpretive rating table for soil structure, so I just gave a class name for each of the classes from poor structure to highly structured, and the corresponding, where it would fit on the curve over here. So that's that indicator. So the next one is rooting depth. So I'm evaluating the soil from 0 to 150 centimeters. Anything greater than 150 centimeters is assigned a score of 0, meaning it's not fragile. It's a good deep soil. And then I'm evaluating a depth to a restrictive layer. And in Nasus, we have a table that contains all the restrictive layers for the profile. And so, and they are root restricted. So root restrictions would be things like bedrock, durapan, petrocalcic, a fragipan, etc. So we evaluate, depth to a restrictive layer. Okay, now the response curve, it's a response curve of crop yield to erosion. So as the soil gets shallower, increasingly severe productivity losses occur under equal erosion rates. So I got this from the literature from Baker. So it's a convex curve. So you can see here, there's no soil gets a rating of 1. Anything over 150 gets a rating of 0. So here's the interpretive table, interpretive ratings for rooting depth. And the rating classes, these rating classes here, I just took those directly out of the Soil Survey Manual. And these were the associated rooting depth limits right here. And then, of course, there's the, the boundary conditions on the scoring curve. Okay, we're going to go to the next one. Okay, vegetative cover. Now, this one was a little tricky in that in Nasus, the only reference to vegetation is the earth cover kind. And that is for each component, we have a field where they can populate earth cover kind, and we have earth cover kind 1 and 2. And so these earth cover kinds come from the NRI. Like, for example, barren land. The definition says that it has less than 5% cover. And they have crop cover, and then they have earth cover kind 2, where you have like row crop and a couple different categories under there. So I just assigned a % cover to each one of those. Now, unfortunately, earth cover kind is not well populated in the database. Maybe 10 to 15% of the soils are populated with an earth cover kind. So in order to use this vegetative cover, if the earth cover kind was null, there's nothing there, then I use the dominant land cover from the USGS land cover database. And I had to go get that and import that into the property. And what I did is I used GCircle and overlaid that with the land cover map and used zonal statistics to get the dominant land cover for the map unit. And then I put that information into the property script. So for each legend map unit key, I would have a land cover that I could use if earth cover kind wasn't populated. So the range is from 0 to 100%, and I use just the standard sigmoid curve. I really couldn't find any relationship there to erosion, even though there probably is one. So let's go down here to the interpretive ratings for vegetative cover. I just used 4 classes, low, moderate, moderately high, and high. And these are the vegetative cover limits. So anything over 80% is considered not fragile. And then varying degrees of fragileness for the rest of the classes. Okay, let's go to the next one.
Kathy, can I ask a question on that, or should I hold it till the end?
Oh, you can ask a question. Let me go back.
So how would this relate to annually tilled cropland?
Well, what I did, there's only a couple categories for cropland, and I just had to assign a cover %, and I just kind of, and it's hard to do because these are static properties. And for cropland in general, if they had nothing else populated for earth cover kind 2, I just assigned it 20%, and I evaluated that over the whole year. And you don't know if they're using cover crops or
Right.
So yeah.
Okay, just curious.
I had to make a judgment call, 20% for that cropland.
But of course, this is Maxine. This is one of the critical ones that the soil health folks and conservation planners can use and work with in terms of adding other aspects to make it a more dynamic system in another sense. For this is just going to be our static general potential, but as we build on this, I see it as a potential to build on for a more dynamic system eventually.
Yeah,
That makes sense.
Yeah, it's getting at more the inherent fragile soil index. It's an inherent, because we're not really working with dynamic properties at this point. Okay, I'm going to move on to slope. Okay, the property that we're using here is percent slope for the component. The scoring curve I got was based on the study by Liu, which was also used in Russell. And so the shape of the curve varies with slope. Up to 9%, you got one shape of the slope. And below 9% slope, the dominant process is sheet erosion, so that has a little different curve. And then from 9 all the way up to 50, the shape is slightly convex. Between 9 and 35%, you got active gully erosion occurring. Greater than 35%, you're prone to mass movement. So slopes greater than 55%, they're assigned 1. Level slopes are assigned 0. So that's how the curve was developed. And if we go down here to the interpretive ratings for slope, the classes, these classes are taken directly out of the Soil Survey Manual. Very steep, steep, moderately steep, all the way to nearly level. And then here's the slope limits for those classes. And then the corresponding, boundary of the scoring curve. Okay, this is the last indicator, and I used aridity and aridity index. Okay, in the database, properties that are used is mean annual precipitation and mean annual air temperature. Those are well-populated fields for each component in the database. So in most aridity indexes, they tend to use evapotranspiration. Well, we don't have that in our database. So I found an aridity index by Martone that just uses mean annual precipitation and mean annual air temperature. And so in his aridity index, it's just the precipitation divided by the mean annual air temperature plus 10. That was very doable with the data in our database. I just used a general sigmoid curve. Less than 5 is a 1, the aridity index. And greater than 30, I said, is being not fragile. So as the index decreases with an increase in aridity. So it goes this way. So that's the aridity index. Let's go down to the interpretation ratings in the rating table. Okay, these classes here, they come from Martone. Those are the classes he developed, and those are the limits that he put on them. I combine the wet and very wet, greater than 30. I put that as not fragile. Anything less than 5, considered highly fragile. So that's how I divvied up the aridity. Okay, now here in the primary rule, this is where we put it all together. When you combine all the indicators together to come to a soil fragility index rating. So we have a rating over here. And so 0, this is primarily 0. I divided it up and I assigned classes to each of the ratings. And I divided them up pretty equally. These index ratings. And so I have 6 classes, not fragile, slightly fragile, moderately fragile, fragile, very fragile, and extremely fragile. And then over here under the description, here's where I attempted to describe the kind of soils that are in each of these classes. And I think I completed the first 3, but I didn't complete the last 3 down here, so I didn't complete this part of the description. So a not fragile soil, they're generally nearly level soils that are deep or very deep. They have organic matter contents greater than 5.7% and are highly structured in the surface layer and have greater than 85% vegetative cover and have a wet or very wet aridity index. So if we go all the way to the extreme, extremely fragile, so an example of soils in that category, they would have poor soil quality in shallow soils with low vegetative cover on steep slopes under very dry conditions. And so poor soil quality is low organic matter and low soil structure, poor soil structure. So a fragile soil, it can have poor soil quality with low vegetative cover on moderately steep or steeper slopes under wet conditions. And I didn't complete these last 3. So those are just examples of the kind of soils that would be in these classes. So this is what it looks like when it's mapped across the United States. Now don't forget the white space. A lot of the west there, that's unmapped areas. And the other white space, I was using GSurgo and then using information generated out of Nasus, and they were taken at 2 points in time, so the legend map unit keys weren't quite matching up. So that's an explanation of why there's so much white space in the middle there, like Missouri, right in here. So don't look at that, just look at the rest of the map. So you're not fragile. Those are your dark greens. You're slightly fragile, lighter greens. And then you're moderately fragile, which covers a lot of the Midwest, a lot of the U.S. Then we got our pinks, which are fragile, over in here. And then the reds, very fragile and extremely fragile. There is some extremely fragile in there. It's just hard to pick them out at this scale. They're mostly in the west, the arid west. So that's what I came up with for the Fragile Soil Index. And that's all I have for the presentation part. So if you have any questions or want to discuss anything, you can always email me with comments if you think of some later.
So Kathy, back on your organic matter, you just used a moderate curve for the Northeast.
Yeah.
What have you done for the rest of the U.S.? What were you using?
For the curve?
For organic matter.
No, I used that for the whole U.S. I was just
Can I send you what? The Cornell was based on the Soil Management Assessment Framework. Can I send you the Excel spreadsheet with those equations?
Yeah, you can do that, yeah. But what I was looking for was the inherent, the maximum potential, probably for the whole U.S.
Right, I know. That's what our equations are based on.
Oh, okay, yeah. But it was applied. That one equation applied to the whole U.S.
Yeah, okay. Well, I don't know whether you should or not, because different soils have inherently different
Yes.
optimal or maximum levels.
Yeah, and it gets at inherent fragility. So the soils that inherently have low organic contents are inherently fragile. It's a little different than soil quality or soil health.
No, I understand that.
Okay.
But what my concern is you're using that same curve across the country.
Yep.
That's not the inherent levels you'd see out west. So I'll send you the curve and you can look at it.
Okay. Yeah. Okay.
Because I'm just a little concerned there. People will see that and says, what, we don't have mollisols or alpha sols.
Yeah. Mhm.
Why do you expect us to ever, comparing us to those alpha sols, northeast alpha sols?
Yeah, it's an inherent fragility. It's just out the west, the soils out in the west are inherently more fragile. Is what I'm saying.
I understand that, but you're still using as a basis organic matter levels that you would see in the northeast.
Yeah. So what are you suggesting?
I will send you what we use in SMAF, which has adjustments for soil type.
Okay.
I mean, the northeast curve is based on SMAF.
Yeah.
The Cornell curve is based on SMAF.
Yeah.
But I'm just a little concerned that you use the northeast as the baseline.
Yeah, so I should be using different curves, is what you're suggesting?
I'm suggesting, just look and see what we have and play with it a little bit. I'll send it to you a little bit in a little bit.
That's great. Mhm.
This is Wade, Kathy. What did you find with respect to bulk density in the literature? Was there anything that would work?
When they referred to fragile soils, usually that wasn't mentioned. The first two things: low organic matter, low aggregate stability.
Mm-hmm.
Not compaction.
I would think that the low porosity, associated with some of the higher bulk densities would be something that you could key on.
Mhm. I mean, we can add another indicator.
And then I'm not sure if flooding is something that you want to consider, or if that's a place you need to go or not. Too much water, and those effects.
Yeah, these are all possibilities. Yeah, this is just what I came up. I mean, there could be other possibilities, yes.
Kathy, this is Jennifer. I was wondering if you could just speak a little bit more about the rankings and your more of the thought process behind the 0.1 and 0.2, 0.3.
Well, I didn't know how to break it up.
Not this rating, sorry. The actual the equation for the fragility index to get this value way at the beginning. Like organic matter is 0.1 and aridity is 0.3.
Oh, you mean the weighting factors?
Yes, sorry. Mm-hmm.
It was just a judgment call. I felt that aridity was the most important. So I weighted it 3 times. Originally, I had them all weighted the same, and I thought that's quite not right. I felt aridity was the most important, and then slope and vegetation. It was just a judgment call. I mean, we can change.
No, I was just curious what you were talking about. Because I'm wondering if about like the autocorrelation between the variables and how that might play into the index overall, meaning like low organic matter and high aridity, or whichever direction it works, but they would be together, right? So I'm wondering.
Yes, that's true. Yes.
I don't know what the answer is, but I was just thinking, like, well, they might be related a little bit, so you almost get, like, double dinged, sort of.
Yeah. Yeah. Because if you have high aridity, you're not going to have high levels of organic matter.
Right.
Probably, you know. Yeah. Yeah, I'm not sure how to handle that.
Yeah. I don't know what the answer is either. And I'm wondering if maybe that's kind of where Diane was going with this, because that model does include a moisture component in developing the algorithm. So I don't know if there's something maybe, with further modifications to better fit the inherentness, because I hear what you're saying about that. There might be some way to integrate both concepts.
Yeah, I'll have to look at that and think about it.